Hi, DARPA SubT. My name is Nick Hudson, and I'm presenting today on behalf of Team CSIRO D61 for the Competitors Summit. Our team's made up of three groups. So CSIRO is leading it, and we're Australia's national research lab. Georgia Tech is doing a lot of our multi-agent autonomy framework. And Emerson is a drone spin-out out of CSIRO doing all the aerial autonomy and providing that platform. So today I'm actually going to talk about a field trip we did recently in lieu of going to the cave circuit event in northern Queensland. And we tried to set up this field test as closely as possible as we could to an actual trial. So it was 20 hours away drive. We brought our fleet there. We made sure that our operators didn't know anything about the cave beforehand. So we had one operator who really hadn't entered the cave system before running the robots. And that was a really valuable decision to make. There's a lot of effort doing this test. And there was quite a few insights we got from seeing, the operators' reactions to operating in a cave. So obviously that's our supervisor, that's Brendan from QUT. And, this is our first robot going out. And I think one of the things that was really interesting in this is the operators essentially launched the drone straight away every time because I think they're so paranoid about the ground being uneven and all these large rocks being everywhere. And you really saw the drone come into its own in terms of a platform because it could traverse really, wide areas, bring back a lot of situational awareness very quickly, which brought down the risk of using the ground vehicles over extremely rough terrain. So clearly this was one of the first times we tested really extreme off-road mobility in a site, that we've never practiced in before. And it was awesome. It was a great experience. There were, a huge sort of chasms that we had to avoid, large embankments, lots of incredibly rough rock. And then we managed to get this team of robots to coordinate themselves. One of the strategies we went with this was to try to be as autonomous as possible. And that's in part because in one of the first runs, one of the operators actually flipped the robot trying to do teleoperation just because they're so unfamiliar with cave environments like this. It's really hard to know what to expect and even understand over a delayed data link. And so we had a really successful trial where we placed the objects beforehand. We had a team go out and place them. So the robots were going out and exploring and trying to find them around these nooks and crannies. They did a lot of autonomous operations over some pretty extreme terrain like that. You just saw of the ground robot going up this big embankment. And then this is, the robots that were able to coordinate each other's motion and go explore to new frontiers and go figure out where to go. That actually worked really well. That was a big change since the urban event, along with the navigation system, to really accommodate all these, expected ravines and big rocks and everything like that. So it was a really valuable field trial, and again, I think we felt that the navigation system worked really well. We did flip a few robots over on occasion. In fact, we never actually ended a run with the ground robots in a operational state. We basically, within about 45 minutes, had explored the extents of the cave that we were allowed to go into. And generally, at around that point or before that point, some of them had been disabled. We'd actually seen a few roll over and keep going. A few just get stuck in really rough tracks. But it was a great test. So I'm sort of going to talk about how we accomplished that and some of the key elements to the approach we took. First of all, I think one of the unique things about our system is both the drone and the UGVs use the same mapping system. So they use this Wildcat SLAM, which I'll talk on a little bit. It's really one of the core parts of our approach. And then both vehicles are obviously capable of detecting objects, which I'm not going to focus on very much today. And then something, as I said, we pushed on really hard since the urban event is the ground mobility, and especially looking at negative obstacles and be able to approach steep ravines and be able to decide if you can drive down them or not. We had a lot of success with that algorithm and really pushed it in this environment. And then also, how do we share those representations and how do we have every robot understanding and collaborating together and doing task allocation. So that's what I'm going to cover today. But first of all, I think another thing we're very proud of on the team is, as I said very early on, we made the decision to make this modular perception system. So on the left here, there's this cat pack, which is basically a spinning LiDAR, which is capable of, has a very wide field of view because it's rotating on an angle, and then it has cameras and a NVIDIA Xavier in it to do all the onboard detection, SLAM mapping. And likewise, the drone has a version of that as well. And one really cool thing is you can just go buy this hover map from Emerson today. So they sell these complete drone autonomy packages. And something that's happened in the last 3 months is CSIRO started the early adopter program for Wildcat, which is a SLAM program. And we actually have several Australian SME companies using this technology and adopting it and trying it out. And so AutoMap, put the link down below, automap.io, you can actually buy this cat pack for ground vehicles now. I think they'll be out, actually sort of shipping in April sort of timeframe. But we put it on a lot of different vehicles. We've tried many different types of platforms in this event. And we're actually using, our favorite one is this BA5 Titan, which is built in Australia 5, the company. And we actually just think it's probably the best ground vehicle in this sort of size class that you can use. We've tried quite a few, but it was really well suited to the cave environment. It was extremely robust, had a lot of traction. It was an incredibly dusty terrain with a lot, very, very slippery areas, just with the amount of dust and build up with everything. And that wide track just allowed you to maintain grip on very steep surfaces you had trouble walking up as a person. So it was a great, anyway, so I think the important point of this slide is in the last 3 months, as I said, you can go buy some of these things off the shelf or very close to it. And we've had a lot of success on the ground side, and we're really enjoying working with these companies. And they've found a lot of excitement sort of seeing their vehicles in there, and we're starting to think about purchasing from our early adopters as opposed to building them ourselves at this point. So I think, as I alluded to earlier, one of the most important things in our approach is that literally every vehicle is computing a global SLAM solution so that they can communicate and pass information around to each other and do task allocation and really understand what tasks are in a rational way. And so because we have these very dense LiDAR clouds, we have the spinning LiDAR, which has a very high field of view, we sort of have to take this, this incredibly rich point cloud and create something, which you can do SLAM with, but also share between agents. And so the fundamental approach for this hasn't changed very much during the DARPA project. It's been a lot of prior work at CSIRO on SLAM, and I presented this slide and the subsequent 2 slides at the interchange in the urban event. But what we're doing is accumulating those raw points into voxels and then calculating higher order statistics, looking at the sphericity or curvature, planarity of the points, and then using those to match up and compute the SLAM solution. So CSIRO invented a continuous time optimization technique many years ago. And essentially what that allows us to do is integrate all those points over, small windows, time buffers like 5 seconds. And so you have this point cloud, and then we're taking this 5-second frame or data window and then computing these circles and rigidly attaching to this frame. And this frame really becomes the sort of unit of communication that we use amongst all of our vehicles in the base station. And so I guess obviously, as you sort of take these 5-second chunks, you can merge them all together using the pose graph, solving the pose graph problem. And you form your initial connections from where the robot drove, how they're that connected. But then over time, you're correcting that based on all the LiDAR data. And you're doing that in what we call the Atlas graph, but it's essentially taking all of these frames from all the agents and computing a global solution on each agent. And what's interesting, obviously, is that not every agent is going to have the same solution. And obviously, that's going to be true if one agent has a subset of the total data that's different than the subset on a second agent, right? You're not probably going to have the same solution. And we don't assume that. what we basically assume is that if we attach information to a frame and a robot has that frame, it knows how to act on it because it can solve for its own global solution with the information it has. And this video sort of shows you an attempt, or it shows you a result that we had in an urban environment before we left for testing, to show how these loop closures occur and how multiple agents share their frames. So each frame here is a different color, and as the agents go away and transmit information between them, they can solve the map. In this case, this was solved on the base station computer, this result, and you can see things changing over time as you get more information and as frames from different agents get merged together. We had a really good result at Urban. We did some analysis on it subsequently to the event. We found we got about 0.03% drift over distance in the Urban scenario that in SATSOT. We've had varying results. It's probably one of the best results we've had, but we were able to determine that from the surveyed points that DARPA put in. So I think if once all these agents have a global SLAM solution, so they have all these frames and they know who produced that frame, the next thing to do is to essentially start attaching targets or frontiers to each of these, right? So each of the robots, as it explores the environment, is computing frontiers. I mean, this is a pretty common idea to look at these frontiers or the boundary of map space and unmapped space. And something that we just recently published was a pretty generic method which looked at the sort of point visibility as an approach. So as opposed to looking at 2D voxels or a 2D grid and computing frontiers, really thinking about the 3D problem. So a drone can explore caverns up high, that there are frontiers on top of tables where you haven't seen, really thinking about generic visibility. And what we do is essentially compute a frontier from a visibility graph and model this frontier surface and then update it and track it over time. And so that's, Jason gave a great talk, and there's a paper at MFI recently on that you can look up. That's online and archive as well. So if you want to go read that, please do. But this is essentially the same algorithm that we ran in Urban, and we found that it translated very well to the cave environment. So we didn't have to do any changes to our frontier code, going from the 2D sort of primarily human geometric, right-angled environments of Urban to completely unstructured cave environments. It generalized really well. And so what you're seeing here is some post-process analysis of the Urban event, where just a single agent is going after and chasing various frontiers, which are represented by these different colors here. So I'm sure a lot of you will recognize this little area. Yeah, and it obviously worked quite well in the Urban event. And it also translated, as I said, to cave pretty well. But something else that I wanted to share was the drone. And so the frontiers are represented a little differently here. They're just these magenta points. But the drone uses the same frontier calculation. It has a different heuristic for what it goes after. So it tends to go after higher frontiers to sort of naturally split them from the ground vehicles. And obviously, it's a lot more capable in terms of reaching frontiers that are in higher elevations. But fundamentally, it's using the same algorithm, with the same type of processing on these point clouds, even though it has different voxel representations and things like that under the hood for its own navigation. So the next thing I'm going to talk about is, once you have frontiers, which are giving you essentially waypoints that you want to get to, you've got to figure out, obviously, how to get there. And something that we overhauled from Urban into the cave scenario is we really focused on negative obstacles. So I think at Urban, DARPA was kind enough to put up rails around drop-offs, both for human safety and, I guess, robot safety. But we really wanted to push on that assumption and, be able to basically drive safely around this kind of landing here, which is on our site, without driving off it, yet still being able to approach the stairwell down here. And so this is essentially the cost map which each robot is generating. And the green cells here are things which are traversable. So the things that you can safely drive on. The magenta elements here are with things we know that are fatal for every single robot. small ground robots, large ground robots, they're just invariantly fatal. So large drop-offs, these sort of handrails here. And then we're left with these orange points, or these virtual surfaces. And we also have a recent, we just submitted to RHEL on this. So we compute this in a voxel map called ohm, and that code's open source. We've pushed the changes back that we ran in Cave to that repository. You can find that in the paper. But essentially, what it's doing is ray tracing to compute these virtual surfaces, or these areas that you haven't seen before. And there's actually a really interesting duality or similarity with frontiers, because again, they're the boundary of space that you've observed and space that you haven't. And so, in this case on the left here, the robot's this orange box, and the dark gray area is this stage that it's sitting on. And then this light gray area is obviously the area that you can't see. It's obscured by the edge of this landing. And so the approach that we took, is we wanted to have this behavior of the robot would drive up, two edges, and as it got closer, this angle, this virtual surface is going to get steeper and steeper and steeper. And at some point, it's finally going to say, no, that's too steep. And something that's really amazing with the BA5 Titan vehicles is they can actually descend 60-degree slopes and ascend 60-degree slopes. We've set that to 45 in our code, but the angle at which you can drive down, you have to get pretty close to the edge. And so we've done a lot of careful design about where the sensor sits and how much is obscured by the front of the vehicle, just so that we can be performant around cliffs and slopes. And this really played a part in the cave scenario, in the cave testing we did, and we'll see some examples of that, where it's really being extremely aggressive about approaching edges. So I'm going to show you a couple examples, and this is from that paper we submitted, and it has a few really good examples here. And so it's getting waypoints, I believe, from the exploration system, and you can see these orange points, are the virtual surfaces, right? So this continuous surface that we're essentially computing in real time, which is what that open source ohm code does. And then the robot can plan up these green, the green surfaces and onto the virtual surfaces, because it believes, it might be okay, right? And so it's trying to get to this waypoint and avoid all the fatal obstacles and overhangs and all the crazy things going on. And it does that by going up this very steep slope. So that slope is actually hard to walk up as a person. And, the robot's trying to get to this waypoint around the corner in this chasm, and it approaches the virtual surface. It's essentially hanging its sensor over the edge, and it's approaching the edge. And you can see we need to be a little more conservative. It's going further down than we probably should be, because slip's going to occur. But eventually gave up and then went away safely. And then this is an example where it continued to actually determine that the subsequent surface went from being virtual to a traversable surface. So even though this is an extremely steep berm, the robot, peeked over the berm, peeked over it, turned in place to avoid some fatal cells, and then drove down the surface safely and continued on its way. So that was a really, really impressive result. I think that was some of the most aggressive terrain I've ever seen a robot autonomously navigate. And it's really, really enabled by being able to rationalize over the surfaces you haven't seen yet, and doing that in a geometric way. So now that we've sort of discussed how we do the navigation, or specifically the cost maps, and thinking about it, what we really want to be able to do is share those maps. As you traverse over an edge and you learn that the surface is now traversable, you really want to be able to share that with the next robot. And so we came up with what we call the topological map. And really what it is the accumulation of these cost maps over time, and then obviously replacing virtual cells with real ones as they appear, and creating a larger subgraph. And then we actually run segmentation on that to create a graph that we can share amongst agents efficiently, with paths that we know are okay to take. So this approach is, it's a pretty, I'm not that familiar with haven't seen this approach done by anybody else, where you're actually forming the graph, which you're doing your global planning on with a segmentation algorithm, as opposed to using some sort of multi-scale or multi-resolution grid. We're literally taking that cost map we determined, putting it into an image, and then running a superpixel algorithm on it to get, group cells, which are both traversable or fatal, but more than that, also of similar slope. And so we really thought a lot about, how do you go up a ramp? And obviously, how do you get samples on that efficiently? And if you think about it as a planar surface, it's pretty easy to cluster those in image space, and that's basically how we seeded or started this global planner. And then we sort of tuned it so that it had about the right properties in terms of vehicle size and was commensurate with that. So we're basically doing that segmentation and getting this type of map out. And then when you put that all together, right, we have these wildcat frames. So you'll probably recognize, I think this is one of the tunnels, the DARPA simulation tunnels that we've been testing with just as a regression test. And here are the wildcat nodes. So these are this white one here and this white one here are root nodes from wildcat. So it's sort of an area that it is seen and it has accumulated data over time in. And then from that, these blocks are a 2.5D height map that's just projected back up into a 3D map. So this is actually a 2.5D map in image space that we're transmitting amongst agents, and then that gets raised back up into 3D for this visualization. And you can see this pixelization or this clustering of areas. And this is the graph that we do our planning on, this green line. And then the frontiers here basically happening on each pathway, and then this robot is choosing, to chase after this frontier, which is this red line. And so this is really the representation that each agent has, and that really allows us to communicate and make decisions in a very coherent way, because you can start thinking like, okay, how long is it going to take me to get to this frontier? And each agent has a very similar representation, assuming it has similar wildcat frames. And so you can do cool things like task allocation in pretty rational ways. And so this is an example in simulation that we put together to sort of demonstrate here. And what you'll see is, I'll just move this out of the way. This agent is chasing after this frontier. And then what actually just happened, I'll just pause it here. I'm fighting this. This agent, I don't know how to get rid of that. This agent, the big agent here, the operator actually put in a task, which was to drop a comms node. So I'll try to play it again. So what's happening is the large robot was going to the right, and the small robot was going to go to the left. And then what happened is the operator said, go drop a comms node just in general. And only the large robot has a comms node on it. So it had to switch to that task. It reneged on the previous explore it was doing. The smaller robot picked up that explore, and now they're essentially allocating themselves, bidding and allocating on these frontiers collaboratively. And so they'll basically be, pitching bids to each other and saying, which one should I go after? And so you see this sort of very harmonious system occur where the robots end up trying to go different ways. And then when they switch, they can switch off tasks and renege them. So unfortunately, yeah, this was a little harder to show in the cave event, both because a few robots got stuck. Our smallest robot 3 tracks quite often. Unfortunately, it just wasn't really coping with that environment. And the large ones did this really well. So we didn't really use a lot of human guidance in the cave trials that we did. We just tried to have them explore autonomously, and it seemed to work really well. And the drone was fully autonomous. So I hope that gives you some insight into the approach we've taken. And I just, wanted to share with you, we've had a really good time as part of this program. These are our team photos, from Styx, Urban, and Cave. And I guess, I don't have failure videos, but I do have some, photos of what we do when you guys aren't around, which is, I guess, mostly crashing robots in caves at the moment, which has been a lot of fun. So really looking forward to seeing everybody in 2021, and I hope everybody's staying safe and having a great time.